So, good morning, everybody. My name is Mae-ling Lokko, and wow. Over the past 15 years, I've been working with husks, stalks, peels, stems, materials that are left on the field once that holy grail, the fruit, has been harvested. Today, they form part of this urgent revolution happening in the building materials sector because these materials have been lauded as a triple heavyweight to fight climate change and address all sorts of things from fair labor to healthy materials in the built environment. But a few years ago, I was working with a fantastic organization in Ghana called Global Mamas. What a name. They were a network of women who began as 6, and they make high-quality textile materials and home-based enterprises. They've grown into the hundreds. They were facing a significant problem, and the local Environmental Protection Agency was coming down incredibly hard on them to sort of treat their wastewater from their dyeing processes. And so they hired my company, Willow, to really look at an affordable, non-toxic solution for treating that effluent. So we turned to this fantastic plant called moringa. It is one of the most nutrient-dense plants on the planet. And having earned the title, the miracle tree, every part of this plant has an incredibly valuable use. It is incredibly resilient, it's efficient, and it grows wild across the region. After you press the moringa seed to get moringa oil, maybe you'll find it at Whole Foods these days, there is something called the press meal, which is a byproduct of that pressing. And we explored its use as an alternative to iron and aluminum flocculants, the things that we use to clean our swimming pools. And this is a fantastic alternative flocculant, which helps all the bad stuff clump together and settle to the bottom. So at the end of a dye shift, a global mama could essentially mix in her moringa press meal into her dye station, let it rest for between 2 to 6 minutes. All that sludge from their worst dye recipes can settle to the bottom. Heavy metals, things, larger particles that cause turbidity, pH changes in water, could all be dealt with well below the EPA guidelines. And then we get sort of cleaner water. But we were also left with that sludge. And how much sludge is bad, you know? Eventually we began to ask ourselves. And although we briefly started to explore the use of that sludge in earth masonry technologies, rammed earth, compressed earth blocks, this question of scale really began to glare at us in the face. So imagine you're getting 2 buckets per woman at the end of a day. Imagine my shock when I come back in 6 months and they've scaled this up in a 200-person factory. Boy, I nearly had a come to Jesus moment. Actually, I did have a come to Jesus moment. And so I began to ask myself a serious question. What if we were not necessarily doing the right thing? There are many ways to do bio the bad way. What if the only thing we were doing was treating the symptoms of a really toxic system? So instead of treating the downstream impacts of what is essentially synthetic color, now diluted in this moringa press meal, what if we could rethink the design of the dyes themselves? And so this question began to shift our approach completely. How would we shift our research if we design materials not simply for what was immediately ahead in the first or second life, but really ultimately, how could these materials impact soil health? So could looking at soil health as the ultimate goal be generative in understanding new processes, new classes of materials? And this has led to a new research area that includes the bio-based, but although bio-based really prioritize where materials are coming from, Soil Sisters, which is the name we've given to this research area, look at where materials are going. And ultimately, this is a broader project, one that is very much about integrating the life cycles of different materials. And it is an ecosystemic project which sees architecture and the complex value chain we've heard about this morning as a form of public health infrastructure. So some of the emerging soil system material classes, which require their own standards, performance criteria, all the way to gaps in their business models in terms of circular design. They include these initial 4, and I'll just show some examples of work we've been doing with that at Yale. This began with carbon sink. These materials essentially we began looking at agricultural residues. This class of materials are going to grow with us as a species. The more we grow, the more food we're going to need to feed ourselves. And as a byproduct, we have a ton of residues, fast-growing biomass, which I think represents some of the world's most undervalued material streams. We produce close to 10 billion tons today as a planet, and 40% of that material is lost somewhere between the farm gate and our plates. They're often combusted on site to make way for a new generation of plant cycles, or they're prematurely downcycled. More than anything, this is dominated by 4 or now big 5 crops: sugar, rice, corn, wheat, and now soy. Over half of everything we grow are one of these plants. So biomass from agriculture is a huge opportunity, primarily because all of these materials sequester carbon as they're growing as plants. And we can actually defer those carbon emissions by burning or downcycling them, by storing them in buildings. So we avoid those carbon emissions now, but we'll have to pay for it later, and there are ways to deal with that carbon in responsible ways. So we started to look primarily, starting with coconut husk, which is a byproduct from a multi-billion-dollar food and cosmetic industry. We've looked at everything from using them as high-density boards, as strong as oak, all the way down to more desiccant materials that are very good at filtering moisture and air pollutants from our indoor air streams. We've also tried to move away from what we've seen these materials mimic in terms of following timber, which is sort of the big brother of all these materials. And we end up what we call Botoxing them so that they don't age, they don't breathe, they look young forever. And it's a huge problem, right? Because we see those drive up carbon, but also huge problems when we think of their degradation into soil at the end of their lives. So eliminating binders, finding bio-based binders, looking at new coatings from these materials can offer another realm of them helping to reduce carbon. If they're designed and effectively integrated into buildings, they can reduce all of our heat gain and humidity patterns that form huge loads on our buildings. We also think it's a huge opportunity to incentivize biodiversity. And so what you see in the middle there, that larger image is coconut husk with corn-fed mycelium, which celebrates the multi-crop diversity of some of the farms that we were working with. We've also taken huge inspiration from fungi, which are, I would say, the plant's best chemists, in thinking about how we might be able to, I'll go back because I just love the fungi growing. Yep, is it gonna grow? Okay, there we go. Fungi have been responsible for bringing plants onto land, helping them form friendships and survive on the planet. They've been essential in returning even our bodies back to the soil. So what could they teach us about cycling materials more responsibly? So looking at non-toxic circular materials, because we can cycle toxicity, we've been trying to also move away from the pattern that we're seeing in terms of fungi materials mimicking the monoculture of plant materials. There are sort of a handful of strains that are commercially produced, and we have millions, close to 10 million fungi strains on the planet, some of which we're not even beginning to understand. So diversifying mycelium and also trying to reduce the embodied carbon that is associated with essentially a lab kind of infrastructure for growing materials. Similarly, with earth masonry, can we also shift some of the binders, particularly cement, which is really what is making a comeback in terms of being a binder in new types of earth masonry, which is driving not just up the carbon footprint, but is also preventing earth masonry from being cycled over and over again as it has been for millennia. We also don't have the luxury of doing away with the muck we've created in terms of textile, plastic, paper, and all sorts of synthetic waste. And so we look at this paradigm of materials called material banks. And this is a way of taking the pressure off our landfills and storing them temporarily in buildings. Essentially, it's a dilution paradigm. But we've been working a lot with textile waste. Where I'm from, Ghana is the second world's leading importer of secondhand clothing. And we know that there's 122 million metric tons of textile waste being produced globally, and that's only going to increase by the end of this decade. And so we've sort of looked at a collaboration of a whole range of geopolymers that replace cement in earth masonry products, rice husk, bioplastics, as well as textile waste to form new catalogs of materials. And lastly, where we all hope to go, regenerative design. And we've primarily been exploring this through color. Looking at all parts of the plant that will generate from its roots, the stems, the petals, will generate a whole host of opportunities for expanding our color catalogs. I'm going to skip through this because you'll hopefully be able to visit our pop-up Carver Color Lab down by the West Barn. But celebrating our work, the work of our collaborator, Sasha DeWare, which is opening up what we call a plantone as opposed to Pantone. Love it. But all the different parts of the plants, mordants, and seasons can shift plant tones. And so we have a plantone for Connecticut, New Haven, as well as our collaborators who are based in Tuskegee in Alabama, 2 plantone catalogs inspired by the work of George Washington Carver. And so I'm going to end there since I'm looking at the timer and out of time. But really, this mobile color lab is an opportunity to bridge academia and community as a sort of mobile education classroom. And it is only one sort of relationship that we're bridging. There's a much larger stakeholder framework that I think many people are going to be talking about today. And it's through these relationships that we can essentially design a new value framework for materials, one that doesn't just happen only at the point of sale, at the first life, but where different components can generate value throughout their life. And that hopefully will offer generative justice, to pervade in our material value chains. So thank you.